Good evening again. This is Professor Triple Nick or Nick PA from Brooklyn, New York. Today is April 8, 2022, about 11 o'clock p.m. I would like to introduce you my lecture about biostatistics and epidemiology board review notes. Let's start from specificity and sensitivity. This is qualities of diagnostic tests. This does not change based on the prevalence or rate of disease in the community. Let's talk about sensitivity. Sensitivity is the likelihood that the test will detect all the people with the disease. Number one, a sensitive test means all the people with the disease should be positive. Number two, a sensitive test means that a negative result excludes that disease in the population. Number four, a perfectly sensitive test. In a perfectly sensitive test, there will be no false negatives. And number four, with a sensitive test, a negative result rule the disease out. Let's go to the next slide, number 2. Sensitivity is if you don't have the disease, you have a positive test. So there is a formula here. Sensitivity is equal to TP over TP plus FN. So basically, true positive over true positive plus false negative. And if we look on figure 5/1, we'll see the relationship between the sensitivity and specificity. We have on the top, the disease could be present or absent. The test could be negative or positive. And we have TP, which is true positive, FP, false positive, FN, false negative, and TN, true negative. Let's discuss specificity. Specificity is the likelihood that the people without a disease are correctly identified as a disease negative. Number one, a specific test means that those with no disease will have a negative test. A specific test means that all the people with positive tests will have the disease. Number three, a positive specific test means a person really has the disease. Number four, a perfectly specific test, there will be no false positive tests. Number six, a specific test, a positive result rule out the disease. Rule the disease in, I'm sorry. Specific, if you don't have a disease, you have a negative test. So there is a formula here. Specificity is equal to Tn over Tn plus Fp. So we're talking about true negative over true negative plus false positive. Hello, I'm back. Let's talk about negative and positive predictive values. This is slide number 3. Negative predictive value or NPV and positive predictive value or PPV. it varies based on the prevalence of the disease in the community population. NPV and PPV start with the test. NPV, the question here is, if you don't have a negative test, what do you likelihood you really don't have the disease? PPV, and the question here is, if you don't have a positive test, what is the likelihood you really do have the disease? Then number 3, sensitivity. If you have the disease, what is the likelihood you will have the positive test? And number 4, specificity. If you don't have the disease, what is the likelihood you have a negative test? The greater the prevalence of the disease, the greater the PPV. The lesser the prevalence of the disease, the greater is NPV. Let's discuss absolute and relative risk reduction. ARR, or absolute risk reduction, is the percentage decrease of the risk of the death and disease from a treatment compared with 100% of the population of the people in a population. Example: every 100 angioplasty procedure performed, one person has major bleeding lead to death. The rate, or the AR attributed risk of fatal complication of angioplasty is 1%, or 0.01. It means that every 100 people we treat, we harm one person. AR is 1%, or 0.01. Relative risk reduction, or RRR, always seems to be much larger number. RRR can be used to exaggerate the effectiveness of the medication. For example, in patients without heart disease and with high LDL levels, the use of statin medication may reduce mortality. Going from 3% mortality to 2% mortality is a reduction of 33%. Let's go to the next slide, which is slide number 4. In this case, we can exaggerate it by saying statin result in a 33% reduction of mortality. Yes, there is a 30% RRR in mortality, but only 1% ARR. Let's talk about standard deviation. Number 1, critical concept for understanding sets of data. Number 2, a must-known fact for the boards. Number 3, SD, 1 SD or standard deviation above the mean indicates your score is better than 84% of the test takers. The standard deviation for the boards is 18 points, for example. You will have to pass 258. It means 240 plus 18 to be better than 84% of the takers. And this is shown on figure 15/2, standard deviation. And when the data is normally distributed, number 1 SD equal to 68% of the scores. Let's go to the next slide. Slide number 5. 2 SDs, this is 95% of the scores. 3 SD is 97.7% of the scores. Following the graphic representation of the effect of SD on the grouping of the data around the mean. The tallest line in the graph shows the smallest SD. So on figure 15/3, we see the effect of SD on the mean. Let's discuss here SEM, which is standard error of the mean. Number one, SE mean means how tightly grouped a set of data is. Number two, SEM is a SD divided by the square root of the number of the samples, or N. Number three, as more samples accumulate, the grouping becomes narrow. This is more precise. Number four, lowercase Greek letter sigma or sigma represent SD. Let's go to the next slide, number 6. And here we are shown on slide 6 on the top how this works. Z-score. Z-score tells you how far above or below of the mean is your score is. Number 2, one standard deviation above the mean, it is a Z-score of 1.0. One SD below the mean is also a Z-score of -1. Number 3, 2 SDs above the mean is Z-score of 2.0. Let's discuss so-called confidence intervals. CI, or confidence interval, assess the precision of the collection of the data. Confidence SI record what either the data points are centralized around the mean or scattered. Number 3, more scatter means less precision. Number 4, when the CI, or confidence intervals, crosses 1, it means that the results are not significant. The 95% of SI, or confidence intervals, then is used basically 2 times SEM. SEM is equal to SD divided by the square root of N, or the number of measurements. Let's go to the next slide. On figure 15/4, we see so-called confidence intervals. N10, N5, N10, and 150. The confidence interval in N10 is 95, in N10 is 95, and N150 is again 95. Let's discuss so-called descriptive statistics. Let's talk about mode, then mean, then median. Mode, this is the most frequently appearing measurements in a set of data points. Example 1, 2, 3, 4, 8, 8, 8, 20, 10. The mode of 8, because of this, is the most frequently measurement. Mean, the average of all the data points in the data collection. Example, in 1, 2, 3, 4, 8, 8, 8, 20, 100, the mean is, or average is 17. It means that take the sum of the data collection, 154, and divide it by the number of the data points, 9, to calculate the mean, 17. Median, the data points halfway between the highest and the lowest in the collection of the management. In a data set above, the mean is 8. It means which of the fifth of 9 data points. Let's go to the next slide, number 8. exactly the middle. This slide number 8, correct for the outliers of the data set. In the normal distribution of data points, the mean, average, the mode most frequent measurement, and the median, the data point of the middle, are the same. And you'll see in figure 5/5, normal distribution. Mean, median, mode, symmetry for 50 to 50%. On figure 15/6, we'll see right sketched distribution. We'll see mode, median, and median, and so-called right sketch distribution. Let's discuss epidemiology terms. Let's talk about incidence. This is the rate in which new disease occur. Let's go to the next slide, number 9. Measure of new numbers of case per unit time. And number 3, medical therapies that lower mortality do not change the incidence of the disease. Let's discuss prevalence. This is the number of the total cases in the population. And number 2, a reduction of mortality increases the prevalence. Let's discuss precision, accuracy, and reliability. Precision, number 1, measurements are immune from randomized. Number 2, data points cluster around one point. Number 3, the opposite is scatter or spread out. Accuracy. This is the combination of sensitivity and specificity. Number 2, equivalent to validity, and sometimes it's true. If something is true, it is accurate. Number 3, gold standard refers to most accurate test. Reliability, reproducibility. If you repeat the measurements, they will come out the same again and again. Number 2 is opposite of drift. Number 3, no necessary accurate. You can also have something comes out reliably wrong. Let's go to the next slide, number 10. Assessing data for more than one group. So-called R, or correctional coefficient. This is, by definition, given numerical value of the level of connection or correlation between two variables or two groups. Number 2, it is very strong correlation. Value is +1. In a very strong inverse correlation, the value is -1. No correlation, the value is 0. We have here on figure 15/7, correlation coefficient variations. We have a positive correlation +1.00, inverse correlation -1.00, and no correlation 0.00. Let's discuss so-called t-test or t-score and ANOVA, ANOVA, or analysis of variance. The two measures, by definition, this is the two measures that assess group of data from different data sets. T-test is used when, number 2, t-test is used when there is two groups of data to assess. Number 3, ANOVA is used when there is 3 or more groups of data to assess. Number 4, both t-test and ANOVA can assess more irregular data set that are not in a normal or bell-shaped Gaussian distribution. Number 5, also used when only a sample of measurement or not all of the value in the entire population is known. And number 6, t-tests answer the question, are the means between these groups different? Let's go to the next slide, number 11. T-square test. Number 1, compare multiple groups for statistical difference. Number 2, used when data is in discrete categories. Number 3, answer the questions, are these groups related or not? Then we have let's discuss so-called study design and analysis of results. Number 1 is RCT or randomized control trial. Number 1, this is the most accurate type of study. Number 2, samples are sorted into different arms of the study by computer or by randomly generated list of assignments. Number 3, avoid selection bias. Number 4, prospective trial. And number 5, if clear harm or clear benefit is evident before the end, the study is stopped by an independent data monitoring group. Let's talk about so-called cohort study. Number 1, observes prospectively over time what happened to group of patients with a certain exposure or underlying illness. Number 2, follow groups of patients or cohorts over the course of years and record incidence of the disease. Number 3, observational and prospective, there is no intervention. And number 5, use a relative risk calculation to assess the results. Let's discuss so-called RR, relative risk. By definition, is used in a cohort study, starting with the asymptomatic group. Number 2, calculates comparative risk of developing of the disease within exposure, vice versa without exposure. Let's go to the next slide, number 12. Case control study. Number 1, this is retrospectively views data, look for the odds of a previous exposure on the developing of a rare disease manifestation. Number 2, starts with people which have the disease and look backwards on other groups which otherwise matched to assess for the risk of exposure. And number 3, subject of recall bias. Let's discuss so-called odds ratio. Number 1, assess case control studies. And number 2, starts with those which have a disease and look for a chance of past exposure. And here we have to discuss a few types of biases. We have number 1, selection bias, which is used less ill patients for the drug end of the trial and sick patients for the placebo side. And number 2, makes the drug look more successful. So-called Baxon bias. Number 1, use hospitalized patients instead of selecting from the general population. And number 2, solve by random selection. Number 3, so-called Hawthorne effect. Number 1, study subjects known that they are being watched for the effect of the drug or intervention. Number 2, solved by a placebo control and blinding both the investigator and the participant. And the last one, this is lead time bias. Let's go to the next slide, which is slide number 13, which is confuses early detection with increased survival based on the treatment. And number 2, can make screening looks like a benefit based on an early detection of minor disease. And let's discuss about type 2 and type 1 and type 2 errors. Type 1 error is a false positive result. It is when a drug or test is said to make a difference when it really doesn't. The other name of is type 2 error is alpha error. Type 1 error means, number 1, rejecting the no hypothesis when it really is true. Number 2, saying a new drug works when it really doesn't. And number 3, saying there is a statistically significant difference in the data when there is really no. Then there is so-called type 2 errors, which is false negative result. The drug or the test is great, but the report saying that it isn't. The other name of type 2 error, this is a beta error. Type 2 error means, number 1, saying the drug does not work when it really does, and number 2, incorrectly concluding that the drug is ineffective. And once again, this is Professor Triple N or Nick PA from Brooklyn, New York. Thank you for your attention. If you have any questions, please feel free to email me. My email is very simple, nickmd1@gmail.com. Thank you. Have a good night.